Okay, as I talked in the beginning of this chapter, we have two different types of compression, that one of them is lossless compression. So using lossless compression, we can represent the symbols with a variable numbers of bits. Okay, in the lossless compression, we can represent the symbols with a variable number of bits. So we can save the average number of bits, and we say that one of the method of less compression is using Huffman code. It means that using Huffman code, we can compress the data. But how can we do that? We use a small number of bits for the most frequently occurring symbols and large number of bits for the less frequently occurring symbols. This variable length code is called Huffman code method. In this method, we have a code tree that consists of nodes connected by branches. So these branches terminates in leaves. Suppose that we have a code tree that describes 4 symbols A, B, C, D like that. I copy it and paste it here. The node at the top of the tree defines its root or starting point. As you see here, this node is a starting point or called root. Now, the branch originates from each node. As you see here, the branch originate from each node. And at each node, we can only have 2 branches. At each node, we have only 2 branches. The left branch is represented with 1, right branch with 0. Okay, we said that branch terminates in leaves, with each leaf representing a valid symbol. So the sequence of bits in a valid code word specifies a unique path from the root to the leaf. Now, this sequence of bits actually specify the symbol at the terminal leaf. I specify A at this code, A, B 01, C 001, and D 000. For example, suppose that N of A is equal to 5, N of B is equal to 2, N of C is equal to 10, N of D is equal to 3, N of E is equal to 1. Now, I want to compress the data using Huffman code. I want to encode these symbols using Huffman code. The first step, that is sort my symbols. If I sort my symbols, I can find that the first one is NC, the second one is NA, the third one is ND, Another one is NB. At the end, I have N. I have to draw the code tree. Now I find that using only one bit, I can represent a symbol. This is my first symbol. How many symbols do I have? 1, 2, 3, 4, 5. M or MX, 5. This is the first bit for the C. Why C? Because the maximum number of repetition is for C. Now I continue. I write the node and again originate 1, 0. Again, I found that here I can draw a leaf. Now, what was the another maximum number of repetition symbol? A. Again, node 1, 0, D. Again, 1, B. In the last one, I can write 0 and draw a leaf here and write E. Now, the code of C is 1. The code of A is 0, 1. The code of D is 0, 0, 1. The code of B is 0, 0, 0, 1. And the code of E is 0, 0, 0, 0. Now, for decoding the Huffman code, suppose that I send this binary sequence. Now, in the destination, I want to decode it. I start at the beginning data of sequence. This is the beginning data of sequence. And continue up to reach to the leaf. It means that 001 is C. Look at here. 001 is C. I start from root. I saw that after 1 I have a leaf, and the symbol of this leaf is A. Again, I have 1 is A. Again, 000 is the another code which is called D. It means that this code represents CBAAD. In the destination, I received CBAAD. Now, after compressing the data, we need to encrypt it. Why? Because these days, with wireless network being accessible to anyone with a Wi-Fi receiver, so it means that data security has become a major concern. So using encryption of data, we can provide the security. We have many different methods for encrypting data. These methods have complex mathematical algorithms. But one of the easiest way of encryption of data is using XOR. So the XOR gate can produce the encrypted data sequence. Now let's talk about this method. Suppose that our source produces a data binary sequence. So, using random variable generators, we produce random binary sequence. We produce the random binary sequence. So, this random binary sequence, which is called RBS, is applied to the actually to data. This RBS is applied to data for encryption at the source, and the same RBS is applied to the encrypted data at the destination to obtain the original data. In other words, we conceal the original data at the source and reveal it at the destination. Look at here. We apply the XOR operation bit by bit. XOR, what was the trust table of XOR for 2-bit? XOR A, B, 0, 0, 0, 1, 1, 0, 1, 1. What was the result, the output of the? Now I have the data, suppose that, like that, 0, 1, 0, 1. Now I produce random binary sequence R, B, S, like that, 1, 1, 0, 0. As you see here, the size of RBS is equal to the size of original data. Now I want to encrypt my data. How can I do that? Using XOR gate. I write encrypted data is equal to DI. This is the symbol of XOR operation. DI XOR with RB. SI bit by bit. Bit by bit. This bit with this one. 1, 1, 0, 0, 1, 0. 0 az qalır. 0, 1, 1, 1, 0, 0, 1, 0. Bit by bit, I XOR my data. Look at here. What is the result? The encryption, the encrypted data, 0 XOR 1, 0 XOR 1, 1. 1 XOR 1, 0. 0 XOR 0, 0. 1 XOR 0, 1. According to the trust table, if I again XOR the encrypted data with the same RBS, in the destination, if I again XOR the encrypted data with RBS, I can find the original data. 1 XOR with 1, 0 XOR with 1, 0 XOR with 0, 1 XOR 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1.